Welcome. I'm here to talk about, and hopefully soon Gillian will be here to talk about. Thankfully, we have divvied up the slides, so her section comes later than mine. So this should work great. We're going to talk about the way that we test our infrastructure automation, also our automation for testing our infrastructure, or as the slides say, our infrastructure testing automation. I'm going to go through, do some intros, let you know who we are, talk a little bit about MySQL at GitHub, and then we're going to talk about backups and restores. We're going to talk about how we do some schema migrations, and we're going to talk about our failovers. The general sense here, the theme in this talk is we're building trust in our automation and our infrastructure, and these are some of the ways that we do it. So I'm Jonah. I manage the database infrastructure team at GitHub. There's 6 people on the team. One of them is Gillian. She'll be here soon. So I think that most of you know what GitHub is. We are the world's largest Octocat sticker and t-shirt company. But that's not all we are. We also have hoodies and coasters and plush Octocats, and there's this software development platform. I think that sometimes it gets more notice than the other things, so I'm illustrating the slides with some of the things that are available now on shop.github.com. At GitHub, MySQL is used for all of the data that isn't Git, essentially. So your code is stored in Git. We have a fairly sophisticated way of storing Git, but then everything that isn't Git, all the metadata, the users, the pull requests, most of the things that you're seeing on the site that aren't code are being stored in MySQL. So we have about 20 MySQL clusters. Some of them have dozens of replicas. Some of them have terabytes of data. Some of them are quite a bit smaller. In general, our setup isn't the largest a lot of us have ever worked on, but it's quite busy. On peak traffic times, we're getting 1 million queries a second. So first up, I want to talk about backups. Backups are super, super important. I'm a big fan of them. We use a tool called Percona Extra Backup to take backups online. We have dedicated replicas in each of our database clusters that do these backups. And then we monitor to make sure that the backups work, right? So what we do here is we monitor success events. And then we trigger off an alert in the event that we don't have success over the last day or so. The idea being, we don't necessarily care if a backup has failed, we care that they're not succeeding. There's some other patterns where we're using something like that later. So I think it's interesting. I'll also note that we'll run backups multiple times a day, so if one of them does fail, and sometimes they do fail, we'll get another one soon, and then that one will succeed, and if that one doesn't succeed, then we'll get this period of time where we haven't had a success, and that's when we'll start looking into it. So really, though, I care more about restores than I do about backups. We test our backups because when we don't test them, we don't actually know that we have them. We have some bits that are over here, and we think that they could be restored. But we have restored them, so we know that they can be. The way that we do this is going through every cluster. We've got a dedicated host that sits there. It pulls the latest backup. It restores it. It catches up in replication. It verifies that things look good. It sends a success event to say, hey, the restore succeeded. and then it moves on to the other. So it looks something like this, but this is actually not how we do it anymore. This is how we used to do it. Now we're using Kubernetes for our restore testing, and the reason here is in part so that we could test the way that we can put data onto Kubernetes clusters, but also so that we can be a little better about our host usage rather than one dedicated server for every cluster. And some of these clusters are fairly small, and the backups don't take very long to restore. We can reuse the same host to do all these restores. So what it looks like is this. The green here is our backup server. It's writing out the snapshot. On one of the clusters, this Kubernetes box comes in. It does the restore. It catches up in replication. It says, great, I'm good. And then it moves on to the next one, does the same thing, says I'm great, and then it moves off to other clusters. So it's not always running restores. We previously were like constantly running restores. These days, I think that the hosts themselves are pretty busy, but not every cluster has a restore running all the time. So sometimes those restores fail, and that's fine, although we don't want them to fail a lot. So what we do here is we'll look into it if they're not working at least once every day or so. This has an added bonus of catching the failures and not alerting us to too many of them, but also if something happens and our auto restore automation isn't working at all, we wouldn't be getting failure events. But we do have a distinct lack of success events in that case. So we'd get something like this. It says, hey, the MySQL 6 testing cluster hasn't gotten a restore in a while. What's up? Can you go look at it? These restores are the same things that we're doing when we're building new hosts, when we're rebuilding old hosts. And we can also kick them off. Wouldn't be a GitHub talk without some chat ops slides, right? So this is Gillian, who has come into the room, kicking off one of these backup restores. Something else that I think is really interesting about these backup restore processes that we have is that they give us information that we wouldn't otherwise have. So, for example, when you really have to restore some data, maybe there's been some big failure, how long is it going to take to get those backups restored? If we're not doing this all the time, we might not know. If we are doing them all the time, we can ask. And we can say, hey, that cluster, how long does that restore take? It'll tell us, oh, well, the last one took about 12 hours, the one before that, a little more, a little less. And it gives us a really nice window into what our recovery times are going to look like. This may or may not have come in very handy recently. So next up, we've got Gillian to talk about some of our schema migrations. Come on up to the stage.
Hello, everyone. So yes, I'm going to talk about our online schema migrations and how we test them. So if some people don't use the terminology that we do, online schema migrations are like an altered table, like adding an index, dropping a column, where the reads and writes of the table can still continue while the process is running. With newer versions of MySQL, this kind of exists built in, but only with certain changes. Prior to that, a lot of companies using MySQL use PT Online Schema Change, which is Percona Toolkit's option, and it uses triggers. So this is a diagram of generally the change management process of PT Online Schema Change, where triggers are put on the original table. They make a copy of that table, run the alter table on it, whatever you want to change, and then have triggers where every insert, update, and delete gets written as well to the new table. And this is fine for a lot of companies. We used to use it. I've used it a lot of previous employers. The problem we had at GitHub is that we have some tables that are so busy that these triggers were causing incredible lock contention because we were having concurrent writes happening to these tables we were migrating, and the extra, like the triggers causing writes on a secondary table, and all the lock requirements of that would cause our database connections to just back up. And then our master database would not be able to take new connections, and then GitHub would go down. So we had some tables back in 2016 that we didn't migrate at all because we knew it would cause this problem. And we also could not, like, if the migration was in play, we could only completely stop it. We couldn't pause it. We couldn't throttle it because those triggers had to be in place, and they were the problem. So in 2016, we created our own tool called gh-ost, GitHub's online schema transmogrifier. And so it's created by our team. It is open source up on GitHub. And instead of using triggers to handle the concurrent changes to the migrated table, we use the binary logs. And so here's a diagram of that change management from gh-ost. Writes happen as usual to the table that we're migrating. All of those writes get written to the binary log, and that's what MySQL replication uses. The replicas read that binary log and execute those writes on their tables. So gh-ost reads from that binary log, parses the writes, and then writes them to the second table that we've created. And so the design implications of this is the binary logs exist not only on the master, but on the replicas if you set it up that way. So we don't have to read the binary log from the master. We can take off some of that load of the master and do sort of the database connection and I/O on the replica, and then only connect to the master to generate those writes. As well, we have control. Because we're reading from a linear log, we have full control of the data flow, how fast and aggressively we write those changes. We can pause it, we can slow it down. We can pause it for days if we want, so long as we still have those binary logs to read from. And because we're writing sequentially, like from the binary logs, there's no lock contention. There's, in terms of the writes going to the original table, there are no connections on the master between the original table and the new table. And so this is just a diagram we have of how gh-ost deals with that. It reads from replica binary log and then writes to the master. And so we created gh-ost, I think we started mid-2016, and it was ready for testing in a few months. And in order to be sure that we could run it on our data and make sure that we don't corrupt anything, we don't lose any data, we decided to test it ourselves. One benefit from being able to read off the replica's binary logs is that we can test entirely on a replica without having to hit the master as well and make sure that the data is correct. So we have this set up in most of our clusters. We have a gh-ost replica replicating off of the master, and we use these replicas for testing both the changes to GitHub's data and whether gh-ost still works with it, as well as testing our branches and new releases of gh-ost. And so this is a diagram of one of our production clusters. In blue is the gh-ost testing cluster, or gh-ost testing host. And so the testing process is just this automated process that's continuously running on these gh-ost servers. It just picks a random table. It runs a basic alter table that doesn't change anything. It just essentially makes a copy of the table. When it's finished that migration, it stops replication, does this checksum comparison between the two tables, reports or success or failure to our chat ops, and then drops that gh-ost table and then starts replication again, and then starts again on another table. And the report for this gets output to our chat ops. So here's an example of one of our robots rooms, this Hubot working away and telling us what he's doing. It shows like one migration result in success, and then there was a checksum failure, so we needed to go look at that. And this just runs continuously, so we can trust from this that Ghost will work great with our systems. And then here's an example. If we have a new branch to test with Ghost, this is the command to deploy the new Ghost code to those Ghost testing hosts, and then just have the testing suite go through it. And so the next thing I was going to talk about is, MySQL cluster failovers and how we test with that. As we've seen in some previous slides, we have clusters with single master, multiple replicas. The replicas exist in multiple data centers, and we also have multi-tiered replication. There will be intermediate masters between the master and a replica with no replicas hanging off of it. And as well, we expect this topology to change. Like between one day and the next, we may see some differences. Some new hosts will be replicating off the backup server, perhaps. There may be a failover. And so in this sort of topology with one master, multiple replicas, our points of failure are the master, as well as those intermediate masters. Because if the intermediate masters go down, then everything behind it is missing those replication rights. So to handle this, we use Orchestrator. It's a tool that has existed for quite a few years. We also work on it, and it is open source. So it's a replication topology management and high availability tool. It does discovery of servers within your topology. It moves them around, refactors the setup, and it also does failovers for us. And our master and intermediate master failovers are automated. We can run them manually, but Orchestrator will sort of watch the cluster. It, I think, pings every host every 5 seconds, but does sort of a global view every single second. If it detects a dead master, like unreachable or it's not responding, it will start a failover process. And it'll take a replica and promote it to master and pull the old master out. We also have some GitHub-specific hooks to make sure that the proxy is updated, DNS is pointing to the right host, run Puppet, and update roles, and as well as reporting to chat ops. So this is an example of a live failover that Orchestrator did without us noticing until it reported it. We do get paged. When a production master fails over, we do get paged for it, but ideally and often the case, we're paged that it happens. We look and see that the new master is running fine, and then we go back to bed. So in this case, Orchestrator, it reports it detected the host. It decided to fail it over, and then it tells us the new master, and then it gives us sort of an audit log if we want to see what happened. And in order to test Orchestrator, we have a specific testing MySQL cluster. We use it for multiple projects that we do, not just for Orchestrator, but Orchestrator does manage it. It doesn't take production data or traffic, but we otherwise have it set up to work as a production cluster in that it has the same operating system, number of hosts, versions. It has replicas in all the data centers, and it's hooked up to our proxy. And so several times a day with this testing cluster, we have scripts that run and just force a failover. So it'll look at the topology. It might move some things just to make it easier to fail over. It'll randomly kill the master either with kill-9 or it'll block the port. It'll then wait for orchestrator to discover the problem and recover, and then it checks for the new master that is in place, the DNS is correct, all the replicas are where they should be, and then it restores the old master from a backup. We know that our backup restores are good because we have it automated, so we trust that with our automation, we can just run the backup restore script within this testing script, and we know it'll be fine. And and then it reports to chat. We have a lot of chat logs. So this is very similar to the previous screenshot. This is one of our testing runs. I think it runs 5 times. Yeah, I think it's 5 times a night. So it just, again, detects that the master is unreachable, decides to fail over, picks a host, fails everything, and then reports it to a log that we can link to if we want. And so generally we know, because of all of these chat logs, we generally expect failovers, the automated failovers, to take about 30 seconds. Like, in production where orchestrator finds, the master's unresponsive, everything will be fixed within 30 seconds, usually 10 or so. It's even faster if we decide to manually fail over a master. And if we do have a failover, we do expect that there was a bit of a glitch, and some people might have seen some unicorns on the site, but we don't expect it to be that long.
So basically what we want to say is you can trust your infrastructure if you can test your infrastructure. You can trust your automation if you can test your automation. Test your backups. If you don't do anything else that we've been talking about here, please test your backups. But also test other key pieces of your infrastructure. Do you have something that's rewriting all of your data? Do you have something that needs to be running properly to keep your site available? Are you building something new that's going to be one of these key systems? And if you are, think about ways that you can make it so that you can test it in ways that are as close to production as the real thing. If you do that, you'll trust your infrastructure as much as we trust ours. Thank you.